So welcome back, and welcome to the second day of this hands-on introduction to deep learning with PyTorch. Do you have any question about yesterday? Something that wasn't clear? Something that we should re-explain maybe later after this presentation? No? Okay. The first set of exercises after this presentation will be essentially very similar and trying to improve on what we saw yesterday. So essentially, we will give you another occasion to go through a similar notebook and do similar things. And so you can, again, ask questions if something is not clear from the convolutional neural networks that we have seen yesterday. Okay, so this morning we will talk a bit more about how to train deep learning models and the problems that sometimes we encounter, and also some tricks to improve the training and the performance of the model. Yesterday we finished by going through the notebook together, and if you remember, we had something like this, where the training loss was going down, and this is expected because it's what we are trying to optimize. And however, we had also a validation set, and this was actually going up after a few epochs. And this is a symptom of overfitting, which essentially happens when the model is too complex compared to the noisiness of the data. And here in this picture, you can see the prototypical case of overfitting, where the dots are actually data that I generated from a cubic polynomial by adding some noise to them. And if we fit them with a linear model, which is this straight line here, obviously it's not a very good model because you have a non-linear data set and you're trying to fit a linear model to it, so you cannot do very well. And then if you try to fit it with a cubic polynomial, which is actually what I used to generate the data, you can do really, really well, as expected. But if you try to fit it with a polynomial of degree 10, you overfit. So you can see that the wobbly lines that are red, apologize, but I just realized that it's not very colorblind friendly. I will change it later. But you can see like the vertical lines are part of a polynomial of degree 10 that passes through all the data points. And you can see that fits the data set perfectly. So the loss would be 0 in this case. But outside of the training points is completely bonkers. So if you try to use the polynomial of degree 10 to predict what's the value of the point here, you will get like a completely wrong value. And this is essentially what's happening with overfitting. And when you train deep learning model, you can look at the training loss and the validation loss. And usually you have overfitting when you have this divergence, because the model becomes better and better and better on the training set, but then it doesn't generalize to unseen data. And this gap between the two is called the generalization error. One thing that you can immediately notice is that at the beginning, the validation loss was actually decreasing. So one very simple technique to prevent overfitting is actually to stop training early on. And this is called the early stopping. Early stopping essentially is just stop training when the validation error reaches a minimum. This is a very simple thing to do, and a trivial implementation of early stopping is essentially to save the best model. So at every iteration, you look at every epoch of your training, you look at the validation loss because you compute it for every epoch. And if the validation loss of the new the model at the new step with the new parameter is better than the model at the previous step, then you save those parameters. And then when you finish the training, when you arrive here, you have overfit your model, but then you can load back the parameters that you had here, and so you have a better model that is less overfit to the training data. This is a very simple implementation. In reality, what you want to do, because sometimes you might have very complicated training trajectories, and the validation loss increases for a bit, but then it starts decreasing again. So what you want to do in practice for like for real applications, what you want to do is to track the loss and maybe stop the training if the loss doesn't improve in 5 epochs or 10 epochs, depending on how long is your training. But the simplest one and very easy to implement is essentially best model. And every time you have a lower validation loss, you save the parameters, and at the end, you can load them back. Yeah?
In statistics, this would be that you have to view points. And also, how does this relate, for example, for the size of the training data set? Because so in real life, normally, you have some freedom generating the training data set, but then the real validation is that from experimental data or whatever. So is that increasing the training data set? Because of course, in the previous example, this was overfitting, but also because you were fitting that points with a...
Yeah, definitely. So later on, there is another technique that is essentially reducing the complexity of your model. But here, what I mentioned yesterday, this validation loss is not your test set, but is essentially a part of the training set that you set aside for validation. The test set you keep completely separate for the validation of the final model. And actually, you can probably, in the exercise, also try what happens if you use the best model or if you use the last model on the training set, and you will see that the accuracy of this model is a bit better because it's not overfitting that much on the data set. But this validation set is what we did yesterday in the notebook. You extract it from the training data. Does that answer your question? Kind of. Maybe I didn't understand it completely, but yeah. So how do you save the best model in PyTorch? And this is a really important thing to be able to do, also because you want to maybe save your model to a file and then reuse it later on. So the learnable parameters, as we have seen, the weight and biases of your deep learning layers are stored within the NN module with the respective NN module class as parameters. And you can have access with the parameters function. You can access the parameters of your model. And this gives you essentially the PyTorch tensor that correspond to the parameters. And because we usually subclass the NN module class when we create our own neural networks, essentially, these model parameters know all the parameters of the submodules, and it goes into all the submodules recursively. And this is why it's very important to always subclass from the NN module, because it's a class that registers automatically these parameters. Then a state dictionary is another construct that is provided by this NN module. And essentially is a map, is a Python dictionary that maps each parameter to the corresponding layer in PyTorch. And so essentially it gives you correspondence between the model and the parameters that then, if you save this state dictionary to a file, you can then load it back into the model, and the right parameters will be loaded into the right layers. And then the optimizer also has a state and is useful to, if you want to save your model and optimizer and then resume training later on. But if you are only interested in the trained model, you just have to save the state dictionary. But it's important to know that the optimizer as well as a state. So in practice, what you can do is that, well, it's very simple. You just get the model state dictionary, and if you want to save it to a file, you call the torch save function, and you give a path of the file where you want to store your parameters. Same for the optimizer, if you want to save the state of the optimizer to a file too. Convention usually use a file ending in .pt or .pth, but this is just a convention. And then if you want to load back the parameters into your model from a file, you can use torch load to load the state dictionary from the file, and then use the load state dict function from the NN module class that actually loads your parameters back in the correct layers of your model. One thing that is very important if you're not saving the state dictionary to a file is that the state dict function returns a reference of the state dictionary. So if you just assign the state dictionary to a temporary variable in your Python program when you are training, the state dictionary is actually updated during the training because it's a reference to the state dictionary within the model. And so you need to use the Python dict copy function to actually create a copy of this dictionary if you want to save it. So you can do the dict copy of the state dictionary and save it into a variable in Python. This is only if you don't want to save into a file. If you save into a file, you don't have to do this because the state dictionary will be updated, but you already saved it to a file, so it doesn't matter. Then another way of reducing overfitting is to add some regularization terms to the loss function, and essentially this restricts the values of the weights of your model that they can take, and this prevents, essentially you have a parameter space that is very big, but you add some constraints to it in order to make it smaller. Very common regularization of the loss function is called L2 regularization, and essentially you are adding to your loss function a second loss that is the square of the sum of the square of all the parameters. And this is so common that is actually included automatically into the weight decay parameter of the optimizer. And this is just because it's a very common regularization technique, and you can actually compute the gradient of this analytically. Is just 2 lambda wj if you're taking the gradient of the L2 with respect to the weight wj. And so you can actually do this regularization when the optimizer is updating the parameters, because when you do optimizer.step, the optimizer goes into all the parameters of the model and updates them, and so you can add this term here as part of that update. And then another quite common regularization is the L1 regularization. It's very similar, but in this case, you don't take the square, but just the absolute value of the weights. And this often leads to sparse models in the sense that many weights will be 0 with this regularization technique. Yeah.
Regularization, you're effectively stopping the weights from going out of some range.
Mm-hmm. Well, I mean, you're adding a constraint, yeah.
You're adding a constraint to the weights. Does it have the effect of, like, if one weight is starting to get too big, does it push other weights? I mean, is it actually added to the gradient descent in a way that...
Yeah, it's actually added in the gradient descent as part of the loss function. So this is why I mentioned that you can compute this gradient quite easily and add it during the optimizer step, but it's part of your loss function. And so the gradient will be the gradient of your loss function with respect to wi plus 2 lambda wi. I mean wj if you're deriving with a specific weight. And you can see it here, actually. In this case, it's not already included in the optimizer, so you have to compute it yourself, essentially. So you can define L1 loss function that takes parameters, and the lambda parameter here, that is a hyperparameter of your model. You decide how strongly you want this loss to be. And then you can loop over the parameters of the model and compute the absolute value with torch.abs, and then sum all of them. And then you return lambda times this loss, and then the total loss of your model will be the normal loss that you would normally use plus this L1 loss. And then when you do backpropagation, you will have the gradients of the loss, the original one, and also the regularization loss automatically. Is this clear? Then, yeah, what we mentioned is already is essentially another technique is that probably your model is has too many parameters, and this is why it can overfit the training set, as, for example, using a polynomial of degree 10 has many more parameters that you actually need. And so one technique is probably like changing your model and redefining your model to have less parameters. And you can compute the number of parameters on a model. This is quite useful by essentially going through all the parameters that require gradient. This is just to make sure that you're only considering the parameters that can actually be fit and are changed during training. And then you can use this num element function that gives you the number of elements in your parameter tensor, and then you just sum the number of elements for all the parameters, and this gives you the number of parameters that your PyTorch model has, if you want to have a look at the actual number. Another regularization technique that is quite simple to implement in PyTorch and is quite useful is to randomly zero some of the elements of the input with probability p. And this happens independently on each channel if you're using, for example, convolutional neural network. And well, the output is also scaled, but what this does is that prevents the co-adaptation of neurons. So essentially at every training step, you're training a slightly different model with some of the neurons, some of the inputs that are zero. And by input, I mean input, not input of the first layer, but input of a given, of the dropout layer in PyTorch. Wherever you put it, it will zero some of the input. And what this does in practice is that it prevents co-adaptation of neurons. So the neural network cannot rely on the data flowing into your network always on the same way, and has to become reliant to losing some of the inputs. And this also improves, is a regularization technique that reduces overfitting. What you can do with this, quite interesting sometimes, is that you can use, sorry, I forgot to mention that this dropout layer, I didn't put the PyTorch function, sorry, but essentially it's nn.dropout, and then as an argument takes the probability of the input being dropped, so this probability p. And this is one of the layers that changes behavior when you do training or when you do inference. During training, you will zero some elements of the input, but when you do inference, you don't. You just use the model as it is. And so when you do model.train, the dropout layers will be active, and when you do model.eval, the dropout layers essentially is like they don't exist. But something that you can do that is quite interesting is use dropout layers during inference to do multiple predictions on the same data. Because essentially when you enable dropout, every time you have a slightly different model, and then you can average the prediction of these slightly different models and compute also the standard deviation. And this gives you some information on how robust is your model on a prediction. Because if you get a very large standard deviation by this technique, essentially it means that the model is not very confident on that prediction because, because the standard deviation is really high, and by changing slightly how the data is propagated into your model, you get very different answers. And it's quite easy to implement. You can just move your data to the CPU and NumPy, your prediction, and have a series of prediction, then use NumPy to essentially compute the mean, or if you want, also the standard deviation. How to implement it in practice? Usually what you can do is to define this enable dropout function that takes your model as input, and then you go through all the modules of your model. I get the name. This is a Python way to get the name of the class. So you get the class name. And if it's a dropout, you actually, you do this during inference. So you put your model in evaluation mode. But then for the dropout layers, you put them back in training mode so that the dropout layer is active. If you only have dropout layers, you can just do model.train, and it works. But if you have also batch normalization layers, for example, that we have seen yesterday, those also have a different behavior between training and inference. And so you don't want to switch them back on. You just want to switch on the dropout. And so this is why you do it this way, because it's robust. This is completely independent of the other layers that have different behavior between training and inference. If you finish the exercise early, you can try to implement it on the notebooks. And then another technique, which maybe answer a bit your question, is that sometimes you don't have a lot of data, or the data is very similar. So sometimes you can actually artificially increase the data you have by doing data augmentation. And essentially, data augmentation artificially inflates the size of your training set by transforming the data at each iteration in a way that it cannot be really distinguished from like the original data set. And in terms of images, usually this boils down to, for example, do random rotations, random translation, or resizing, or flipping the image. So in this case, you essentially inflate the size of your data set, and is different at every epoch. And obviously, this helps reducing overfitting, because you have more data, artificially more data to train. And in PyTorch, especially Torch Vision for images that we used before, what you do is that you can add this kind of data augmentation to the transformation. So before, we only used the two tensor and then the normalization. But now, between the two tensor and the normalized, you can add some transformations that are provided by the Torch Vision library. For example, random resize and crop, and random horizontal flip. And this transformation will be applied on the fly every time you get a new batch of data. The resize transformation is also quite helpful if the size of your image is not what the model expects. If the model is not being created to be a bit independent of the size of the input, if you expect like a very specific input, you can use the random resize to resize the image to have the correct. And you can see a whole bunch of transforms on PyTorch documentation, so you can play with them. Yep.
Is there a way to make these results reproducible reproducible, or is it going to be random each time you train?
It's a very good question. So usually also in the previous notebook, you have random results because the weight initialization of the model is also random. I think I can show you it later, but I think in one of the notebooks, the generative ones, you can set essentially the seed of your random number generators. You have to do it for the PyTorch random number generator, and oftentimes you use NumPy as well under the hood. And I think maybe some of this, this is already in PyTorch, but it's good practice to also set the NumPy random number generator. So essentially you set a seed for the random numbers generators. And in that case, then you always reproduce the same random number, so you produce the same result. But also for the model as well. Like if you don't have this transformation, it seems, the loading of the data that the model sees is always the same, but then the model is different every time you run the notebook because of the random initialization of the weights. Another technique that can be useful if your model is struggling to train is to use an adaptive learning rate. Before we've seen there's a fixed learning rate, which is the parameter of the optimizer, but it might be non-optimal for the whole of the training, also because the gradients change quite a lot during the training. And in PyTorch, the learning rate can be adjusted during training based on the number of epochs, for example, or based on some validation metrics. So, for example, this reduced learning rate on plateau keeps track of the validation loss, and if the validation loss reaches a plateau, can modify the learning rate in order to essentially escape this plateau. And there are plenty of schedulers. You can see them in the documentation, PyTorch Optim, essentially. They are in the Optim module of PyTorch, and here I give a simple example of an exponential learning rate scheduler that essentially makes your learning rate decay exponentially during training. You define the optimizer as usual, and now you have to interpret the learning rate as the initial one. Essentially, this is the initial learning rate that you start with. Momentum we will discuss in a bit. And then you can define this exponential learning rate scheduler, which is linked to your optimizer because he has to know which optimizer has to change the learning rate of. And then the gamma parameter is your exponential decay parameter. And then what you do during training, you have the usual training loop epochs over the mini batches. You zero the gradient, compute the output, loss function backward, optimization step. And then at the end of the epoch, here I do it every epoch, but you can implement it to do it every 5 epochs, 10 epochs, whatever you want. You can do scheduler.step, and this applies this exponential decay to the learning rate. So after the scheduler.step, the learning rate of the optimizer for the next pass will be different and lower. And then, optimizers, there are a whole bunch of them, and it's a whole topic on its own. But just to explain what this momentum parameter is, essentially, yesterday we have seen that the stochastic gradient descent is just updating your parameters with the gradient of the loss with respect to that parameter. And you have this is the learning rate. What you do when you use the technique that is called momentum, essentially you keep a running estimate of the gradient that is based on the history. So you not only have the current gradient, but you also have a term that comes from the previously computed gradients. And this beta parameter is this momentum parameter here that, again, is a hyperparameter of your model. And so there is some freedom of choice, but it will impact your training. And what this does essentially is that you can get away from or get quicker, for example, on valleys of your loss function, because if the gradient is really small in the original, well, in the simple implementation, you take very, very small steps, unless you have an adaptive learning rate that you can change. But in this case, if you have the history of the gradient, maybe you just came from very high gradients, and so you still have some momentum that pushes you quicker through very flat valleys. So maybe this gradient is very small, but you still have a bit of push coming from this term here when you update your weights. And yeah, as I mentioned, there are a lot of different optimizers. Yesterday we have seen the Adam optimizer in the notebooks. It uses these techniques and a few other techniques to actually improve the training. Is a whole topic, so we don't go too much into the details here, but it's important to know what this momentum parameter. And actually, this momentum parameter, we didn't look at it, but it's also part of the stochastic gradient descent. So you can apply this technique to stochastic gradient descent as well, and it is actually applied by default in PyTorch. So if you want the very simple thing, you actually need to set this momentum parameter to 0. And you can explore with it in the notebooks. Then another big topic is weight initialization. So how do you initialize the weights of your model? And here we have a very nice XKCD comic where essentially it shows that the neural network is a pile of linear algebra where you put your input data and you collect the answer on the other side. And if the answer is not good, you just steer the pile to make it look good. And this is a very comic description of the learning loop in deep learning. But yeah, how you initialize this pile of linear algebra depends on the weights that are randomly initialized at the beginning, and you can initialize from different distribution, and obviously this has an impact on training. We'll not look too much into this because the defaults of PyTorch are usually reasonable, but maybe something that you want to look for very deep model, or maybe something you need if you want to reproduce a paper where they say, oh, we actually initialize the weights in this way. You want to be able to do that in the same way. And yeah. So how do you initialize the weights manually in PyTorch? Essentially, you need to define a custom weight initializing function. The name is completely arbitrary, but it takes your model or an NN module as input, and then you can look what the module is with the Python isInstance function, for example, and do different initialization for different layers of your model. So maybe the linear layer, you want to set the bias to 0 and get the weights from a normal distribution, while maybe for the convolutional layers, you want a different uniform distribution, and so you can actually apply different distribution to different layers as you want. Essentially, you can build this function to do the initialization you want. What is probably interesting is that you can access the weight parameter of your module doing module.weight.data. So this gives you like the tensor that represents your weight parameter. And then there are some functions like normal is a function that modifies in place the tensor, so you can actually use it. Is already, or 0 as well. It's the same thing. You for the bias you do module.bias.data and you access the tensor that represent the bias unit in your linear model, and then you can do .0, which is a 0 function of the tensor that modifies the tensor in place. While for more complex distribution, they're not part of the tensor interface, but they are stored in nn.init. So there is a whole PyTorch init module that contains common distribution for initializing your data. And in this case, it's still modified in place. Actually, the last underscore in a function in PyTorch means that it modifies the data in place. So you see we don't have any output here, but then you pass the module.wait.data and it modifies the data in place and initializes it to this Xavier uniform distribution. And then, yeah, once you have this function defined, you can actually apply it to the model. And after you apply it, the model will have the weights initialized according to the distributions that you defined there. Then another big topic that is super useful if you're working with deep learning model is transfer learning and fine-tuning. And the motivation is that training deep learning models can be very expensive. If you think, for example, at the large language models that you hear about today, they take weeks or months to train on multiple GPUs or supercomputers like the ones we have here. And so you don't really want to do that every time for every new task. And also, there is an observation that many tasks are closely related to each other, so you can probably reuse part of a trained model to work on a similar or related task. Some data sets are too small to train a very deep neural network because of the overfitting, for example, that we discussed before, or you just cannot learn anything from a small amount of data. But what you can maybe do is, for example, using a pre-trained model that has been trained on a huge amount of data and then fine-tune it for your small data set. And the other thing is that random initialization is often not optimal. And so even if you want to retrain the whole model from scratch, instead of having randomly initialized weights, you can use weights that are already trained on a similar or related task. So you don't start from completely random from scratch every time. And so the techniques of transfer learning and fine-tuning aim to reuse pre-trained model and fine-tune them for the specific task at hand. And this is really useful, especially if you're just playing with models. You can reuse pre-trained models and play with them quite easily. So in the CNN example, for example, that we have seen yesterday, CNN for classification, if you remember the slides, in CNN we have essentially two conceptual building blocks. You have the first building block that is a bunch of convolutional layers that, as we've seen yesterday, essentially act as a feature extractor. So extract some important features from the image as the convolutional filters are learned. And then you flatten all these features, and then you use a feed-forward neural network to classify. So essentially, these two building blocks are quite distinct. One extracts features from images, and the other uses those features to do a classification task. And so what people realize is that, well, the feature extraction layers in very big models that have been trained on very big data set of images are actually quite useful, and they learn to extract like very general features from images, and so you can potentially reuse those features for your task with images, for example, classification. But if you want a different data set, you will have to change the classifier and retrain it for the task at hand. So you can take the first part of a pre-trained big convolutional neural network and then just change the last part that does the classification. So for example, you can think about a model that comes from the ImageNet competition that we discussed yesterday. And in the ImageNet competition, there are 1,000 classes, but maybe you want to apply it to the CFAR dataset that only has 10 classes, as we've seen yesterday. You can actually reuse the feature extraction from the pre-trained model and then have a classifier that you retrain on the classification problem with 10 classes. So you just change essentially the number of outputs and train some of the last layers. So how does it work in practice? The first thing that I want to show you is how to load pre-trained model from Torch Vision, which is this PyTorch module to work from images that we already seen yesterday, and is the one that contains all the transformations, for example. And it comes with a models module, and the models module actually contains a definition of famous convolutional neural network architectures, but also pre-trained weights. And it's quite easy to just import the model. You can just, from models, import ResNet 50. So you have access to this ResNet 50 CNN architecture. And then you can import it with pre-trained weights. So you can set the weights parameter to whatever weights you want. For example, this is the ImageNet 1K version 2. So it's the version 2 of the pre-trained network on ImageNet with 1,000 classes. Is also the default, so you can, there are many pre-trained parameters usually, but you can select the default, and you can also pass a string with the name of the parameters for convenience if you don't want to import this. And then if you just want the model and you don't want the pre-trained weights, you can just say weights equal none, and you just get the model architecture, but with randomly initialized weights, and so you have to retrain it from scratch, essentially. PyTorch comes with what is called a PyTorch hub, and is an easy way to support publishing models and pre-trained weights, so that actually you can build your model, put the pre-trained weight somewhere, and then make it really easily accessible from other people to use. And what you just need to do is to put this hubconfig.py file on GitHub. I don't know if it works also with GitLab. That's to be found out. But essentially, you define this. You can define a myModel function that essentially returns the model architecture, and also train this pre-trained parameter, for example, where you can load the weights. And PyTorch, torch.hub comes with some utility function like this one, load static from URL, so that you can essentially put your PyTorch weights somewhere else, not on your GitHub, because it's limited to, I think, 100 megabytes. But some of the weight files are actually gigabytes large. So you can put them somewhere on the internet and then use this load static from URL to automatically download this pre-trained weight, load them into your model, and then return the model with pre-trained weights. So this is a very nice way of making your model that you have on GitHub available to everyone else. Because then, if your repo has this file and this definition, you can essentially just do torchhub.load, give the path to the repo, and then the name of the model, which is essentially which function to call that returns a model, and then the parameters to pass to this function. So for example, pre-trained true will return, will load the weights, and while if you do pre-trained false, it will just instantiate the model and return it with randomly initialized weight. So it's a very nice way to make your model easily available to other people. And this is how the Torch Hub works, essentially.
Yesterday, for example, we trained our CNN with 64 channels, and then we used those channels as features.
Yes.
does one usually just take the whole convolutional block, all 61 channels, or can you sort of iterate over the individual channels and see what they react to, and then cut them, cut and paste? Do people generally just use the whole thing?
Well, generally, yes, but you can definitely do what you mentioned. You can also try to unfreeze, like, for example, I will show you in a bit, but you usually freeze all the parameters of your model apart from the last layer, and then you can train a bit, and if it doesn't work very well for your model, you can start unfreezing the layer next up and next up. It's...
I could freeze those, so I could add 5 or 6 more and then carry on training.
Yeah, exactly. Yeah. This was the slide I was mentioning. Essentially, if you want to just reuse a part of the model or the entire model, but you don't want to train it, as we discussed in PyTorch, AutoGrad essentially automatically computes the gradients of the parameters of the model. But under the hood, essentially, they have this required grad attribute that is set to true automatically because they're model parameters. So by default, you want to train them. But if you set it to false, then the AutoGrad will not compute the gradients of those parameters. And so they will not be updated during the optimizer step. So this is called freezing the model parameters because they're not touched by the optimization anymore if you set this required grad to false. And so if you want to freeze the whole model, you can do model, well, convnet. You can do name of your model dot parameters, loop over them, and then set all the required grads to false. But you can also do it selectively. So for example, you can take a subset of this list and only freeze. For example, you can go from 0 to -5. So you freeze everything apart from the last 5 layers. Or you can actually do it manually. As we've seen before, you can do model.layer.data.weights. And then the weights will have this required grad. So sorry, maybe it's clearer if I show this. But you could potentially do module.weight dot requires grad equal false. So you can freeze whichever layers you want, essentially. Yeah, so this is about freezing and how does it work in practice. Let's consider that you have a sequential model that is just made of linear, ReLU, linear, ReLU, linear, and you can figure out that probably is something that works on MNIST because the input data is 28 by 28, which is the size of images in the MNIST or fashion MNIST dataset. And then you can maybe imagine that I took inspiration from a classification model with 10 classes because the output of the last linear layer is 10. And then if you print the model, you can see that when you define this model, the sequential, but also if you do the NN module subclassing, this will be taken from how you define the forward pass, but you can print the model, and you can see that they're all indexed. So the first linear layer is 0, ReLU is 1, linear is 2, ReLU is 3, and linear is 4. So what you can do is that you can freeze all the model parameters, and actually this is what I was mentioned before. In this case, you don't freeze all of them, but you freeze the ones, all but the last one. So essentially, this one is not frozen, but this one is frozen. This one doesn't have any parameters, so this doesn't do anything. And this is frozen with this function here. And then what you can do here, let's say that you don't want to have a classification with 10 classes, but you have a related data set. Maybe you have a subset of MNIST with numbers from 0 to 5. So you cannot use this model because, you can and you just don't predict the other classes, but let's assume that you only want the probability of the numbers from 0 to 5. then this also returns you the probabilities from 6 to 9. And you can change it to only output 5 classes. So this is what you want to do. Let's assume that this is what you want to do. So what you can do is that you can take programmatically the number of features that are input of the last linear layer, and you can just do model -1, which returns you the last layer, so this layer index 4, and then access the in features attribute, and this gives you essentially 64. And then you define a linear layer that takes 64 inputs so that it works really well with the output of the previous layer. And then you just define 5 instead of 10 so that it outputs 5 probabilities. Well, probabilities for 5 classes. And then once you have this linear layer defined, you can actually assign it to your model. Here we use -1, but if you use 4, is the same thing. And so essentially this linear layer will be swapped with this one. And if this is a pre-trained model, now you have the frozen parameters on this layer, frozen parameters on this layer, and then you have a new linear layer that is unfrozen. And so if you retrain with this model, essentially only the parameters of the last linear layer will be updated. Is this clear? Yeah.
So here we're modifying in place the architecture, but if we add something new, we also have to change this forward function that we're finding.
Yes. So essentially here is very simple because you have the sequential API. But if you have your NN module as a class, then you have to modify the forward function. Yeah. What you usually do, for example, is that this goes back to what I was mentioning yesterday of building your models in blocks. I don't know if I have an example here. No. I can maybe show. It's maybe worth to show. So if we look at the VGGNet in PyTorch source. Oh, this is not the actual implementation. Oh, this one should be. Yes, okay, so this one. This is the actual implementation of VGGNet, I think. And this is built in a modular. Can you see, or should I put it a bit more? This is the actual implementation of VGGNet. It looks complicated, but if you look closely, well, we have the init function that we know, and then we have the forward function. And in the init function, what you have is something that is a sequential model that is called classifier, and then a feature extraction module that essentially is features. So this is not the full implementation because the first part of features actually changes, and we can probably see later on if we. Yeah, it doesn't contain the whole thing that I wanted to show, but essentially, wait, can probably. This is probably easier. Okay, and then we can do VGG. Well, our model is an instance of this VGG16. I think we don't have to pass any parameter. Okay, and then if we print, if we print the model, can you see? Yeah. Yeah, if you print this model, is what I was trying to show you before, but it didn't add the feature part. But you can see that the structure is a bit more involved than what we had in the simple sequential model. Here is just a list of layers. While if you look here, we have a features attribute that contains a sequential model, and then the sequential model is just a list of layers. And by the way, this is like what deep neural network look like, so it's a bit more complicated than what we had in the exercises, but you can recognize all the layers. But essentially, you have this features attribute that is itself a sequential model. Then you have an average pooling, and then you have another attribute classifier that is a sequential model. So if you wanted to reuse VGGNet in your own architecture, you can actually use only the features one. So if you do model.features, you see that you only get the first sequential model. So if you were to define your model where you only want to use the convolutions, you just essentially use well, I don't want to implement everything because it will take a while, but you can extract just this part and use this one in your forward pass. And if you look at the actual definition, you see that the forward pass has been simplified a lot with this structure, because you define the features as a sequential model, and you define the classifier also as a sequential model here, and then your forward pass can simply be x equals self.features, which is a sequential model. Then you do the pooling, then you do the flatten, so it's the usual thing, and then you do the classifier. So instead of having like a huge forward function, you have a much cleaner one, because you built your model in blocks. And so to answer your question of what to do if you want to add layers on, essentially you would just take these features from VGGNet, and then in your forward pass you would have x equals self.features, and then the flattening, and then you can add your own layers. You can define them in the init constructor, and then just use them in the forward pass, as we did in the exercise. Is this clear? Okay. Yeah, then there is a whole big topic that we kind of touched already about hyperparameter tuning, because hyperparameter are essentially something that is not trained, so it doesn't change during training, but it still affects the performance of your model. And usually in the notebooks that we see in this class, we set the hyperparameters to sensible values that we know work. But there is a whole field of hyperparameter tuning, so how to automatically or semi-automatically find the best hyperparameters. It's very expensive, because every time you choose a hyperparameter, you need to train the model with that hyperparameter, and the hyperparameter space can be huge. And there are some libraries to essentially do this as efficiently as possible and in an automated way. Famous one of Raytune, Optuna, HyperOpt, which usually all of them take a function that does the model definition, training, everything, and returns or stores the accuracy while you train. And so they can actually do things in parallel and train many models in parallel if you have access to supercomputers like we have here. So they're really interesting library to look into, but we will not go into details here. Just wanted to mention that they exist and they can be very useful in practice because, yeah, it's often difficult to guess the hyperparameters, or it's a lot of trial and error, and this automates a bit the search of the hyperparameter space. And then, yeah, one thing that is interesting, we will not touch it here in this class because it's hands-on and you have to learn how to build your model from scratch. But as you already probably realized, PyTorch is rather bare-bones. So we had to implement the training loop by hand, implement the validation loop by hand, implement the inference loop by hand, and so on and so forth. And so there are many libraries that is actually built on top of it and require much less boilerplate code. So you can get started. You can think about the architecture and what you want to do and your problem, how you want to solve it with which architecture, but then you don't have to think how to implement the training loop, or I forgot to zero the gradients and stuff like that. So it's quite useful to get started quickly on project. One of them is PyTorch Ignite, which is part of the PyTorch framework. It's very lightweight. Then there is FastAI. It's another one that I didn't look into it. And then there is Keras 3, which is Keras is a very, very famous one because Keras 1 was a library for like a common API for different deep learning libraries that existed in the past. Oh, sorry, that existed in the past, and then I think Keras 2.0 has been completely integrated into TensorFlow. And now with Keras 3, it went back to the origins, and now it supports different backends. So essentially, you write one single code that can work with PyTorch TensorFlow tensors and JAX tensors, essentially. And the different deep learning, these are other deep learning libraries that have different capabilities or different, well, I mean, there are different deep learning libraries, so you might want one of the other. Maybe there are some advantages of using one of them instead of PyTorch, and Keras allows you to write your model once and then essentially reuse the code with different backends. And just to show you, to whet your appetite to use this kind of libraries when you finish this class, this is what the training loop for a supervised training classifier looks like. Very simple compared to what we wrote in the notebooks. This is with PyTorch Ignite. You can import a create supervised trainer function, and you pass model, optimizer, loss function, and the device on which you want to run. This creates a trainer object, and then you can just do trainer.run. You pass the train loader, which is what you load the data with, that gives the mini batches, and then you say for how many number of epochs you want to run it. And this runs the training. So much less boilerplate code than we have in the notebooks. It's very good to know what's going on behind this, and you actually know, because it's what we do in the notebooks, but in practice it's very nice to use this kind of libraries so you can get started really quickly. And PyTorch Ignite is very flexible. So for example, if you have this is the default training step that is used, and you can see you can recognize it really quickly. You put the model in training mode, zero the gradients. So this is the first two things that you should remember to do, otherwise things go wrong. Get the input and get the input and the labels, compute the prediction, compute the loss function, backward pass, optimize a step. And then, in this case, you return the loss so that PyTorch Ignite can interact with it. And then once you have the training step, you can create an engine object, and then you do trainer.run. So it's a bit more code than this one. It actually is what this one does under the hood. But this means that you can focus on just creating the training step and forget about the epochs and loop over the batches and stuff like that. This is done by PyTorch Ignite automatically. And then you can build on top of this with many more features. And then similar example for Keras. Keras has its own API for writing the model, so it's a bit different from PyTorch. But you can see that the libraries are very similar. So you have an input layer, and then you have a conv2d layer that is very similar, takes a number of output channels. It doesn't take the input, figures it out automatically. And then the activation can be defined as part of the conv2. So it's a slightly different, but you can define essentially the same sequential model. And also the names are very similar. Keras.sequential, before we used nn.sequential. For PyTorch, layers.conv2d, the only thing that changes is the capital D. Max pooling 2D, you've seen this before. Flatten, you've seen this before. The only thing that is slightly different for historical reason is that the linear model is called dense. But essentially, you can already recognize all the building blocks, I think. Yeah, and you can set the soft max activation at the end, so you know that this is a model for classification. And again, with Keras, very simple to define the training loop and actually run it. You can do model.compile. You pass a loss function, an optimizer, and a metric that you want to compute during the optimization. Obviously, the optimization always uses the loss function, but then in parallel, you can compute other metrics like the accuracy. And then you do model.fit. You pass your training data, batch size, epochs, validation split. So this is also very interesting. It does the validation split automatically, so you don't have to implement it yourself as we did yesterday with the random subsampler and scikit-learn. Just as everything inside here, and also evaluation of the model can be done really quickly on the test set. This is very convenient libraries to avoid writing all the boilerplate code that we are writing now just to learn, but then in practice you would use one of those libraries to get up to speed quickly. Yeah, so this concludes the overview of training techniques and libraries that might be useful. And for the exercises, maybe we'll have breakfast first. Yeah, it's 10, so we can have a break for breakfast, coffee. There are some croissants outside. And then come back for the exercises, where in the first one, very similar notebook to the CNN one that we've seen yesterday. So you can reuse most of the things. But the thing that we will also do is use dropout layers and see their effect on training, and also data augmentation and see their effect on training. And also you can play with saving and loading the model weights into the model. And then there is another notebook. I mean, it's the first time we do this course, so it's very difficult to judge how long it takes to go through the exercises. So maybe this is optional. I don't know how long it takes to go through this one. But there is also a second notebook where you do transfer learning with VGGNet, which is the deep learning network that I showed before, where you want to reuse a big chunk of the architecture, but then this predicts the probabilities for 1,000 classes, and we want to apply to a problem with 5 classes, and those 5 classes were not in the ImageNet dataset. And what you will have to do in this notebook is essentially freeze the VGNet parameters, and then modify, as I showed you before, the last layers to have new linear layers that output 5 classes, and then try to see which kind of performance you get with a. The data set also is very small, so you could not train the whole deep learning architecture on that data set. So it's quite, it's an application of the transfer learning technique that we discussed. Yeah. Okay, so we can go through the first notebook. And then I can correct we can go through the next one later on after some time. So, the first part is the usual thing that where we load all the libraries, and And then, yeah, I put some link to have a look at the V1 versus V2 transforms in Torch Vision that we discussed during the class. But essentially, if you're using version V2, you can convert your pale image into a tensor and then add some data augmentation. So for example, this random horizontal flip transformation and this random affine transformation to translate and rotate the image randomly. And this transformation are applied on the fly when you get one batch of the data. Do you have any question about this data augmentation? Yeah.
Does it make any difference to specify the type for
The D-type before the flipping? I don't think so. Yeah. But I should double check. Yeah.
You get away with plot 60?
Well, by default, all the parameter models are in float 32, so you should use the same thing. But then you could theoretically change the default of all your the type of your model parameters, and then in that case, you can use the same floating point type. Yeah. Any other question about this data augmentation?
So transform for normalize has to be the last command, right?
It doesn't have to be, but you need the floating point D type. So the normalize has to be applied on floating points. So it has to be later than the conversion from integers to floating points. Okay. And then later on in the notebook, essentially we define another transform, but doesn't have the data augmentation. So you just take the image, convert the type, and normalize. So we have an augmented train set, which is essentially CFAR with this transform augmentation. And then we have another train set that doesn't have this, this augmentation. And then the test set is essentially, yeah, same transform without any augmentation. Yeah.
In one of the examples before, we had the two tensor instead of two image.
Yes, that's the difference between the V1 versus V2 API. There are two slides from yesterday, I think. Yeah, before it was two tensor. You can still use the two tensor. That actually the two tensor does the two image and 2D type automatically, and the scaling as well. So it's a bit less transparent, and this is why in V2 they essentially split it. But you can still use V1 if you want to. I'm showing V2 just because probably at some point V1 will disappear and V2 will become the norm, and so probably at some point the old way will not work with new versions of Torch Visions. Then you define again the subset random sampler to sample to essentially subdivide your training and validation set. I mean, you do it here with scikit-learn train test split, and then you define based on those indices random subsampler that actually randomly subsample this data set when you ask for a batch. So this is the same as previously. The only thing is that now we have an augmented train loader with the augmented train set, and then the train loader with the train set. And then if you visualize the data, this part of the code is the same as before, but you can see that there are images that are randomly rotated and translated, like this one. Then for the convolutional neural network, I kind of did it in the same way that we discussed this morning during the lecture, of doing two different blocks, one for the convolutions and one for the classifier part that is feed-forward neural network. And so you can define your conv attribute. I mean, this name can be whatever you want. In the previous example, like in the VGGNet, this is called features. So you can call it however you want, but it's defined as a sequential model. And if you use the sequential model, you have to define all the layers one after the other. Because what the sequential class does is that takes an input, pass it to one layer, takes the output of the layer, and pass it to the next layer. So you have that your input tensor goes to the first convolution, first ReLU, pooling, convolution, ReLU, pooling, and so on and so forth. And likewise, same thing for sequential. And you can define dropout, linear, ReLU, dropout, linear, and the log softmax.
I have a question.
Yeah.
Does it make a difference if you apply log softmax inside the sequential or right after applying the fully connected layers?
No, it doesn't. So you can choose if you want to apply it here. I mean, if you want to define it as part of your sequential, or if you don't have it, like this, then you can do x equal the usual functional API log softmax, and then x dim equal 1. Exactly the same thing. The only thing that I think might not happen is that if you print the model in this way, we discussed with someone before, you don't see the log softmax. Because when you print the model, it just prints essentially the NN layers that you define in the constructor. But this is the only difference. Like, technically, it's not different, and you can decide what to do. And yeah, maybe something else to mention is that the things that are part of the NN module have camel case names. So the log softmax, L is capital and softmax is capital, and they're attached together. And the functional API has everything in lowercase and then with the underscore. And yeah, usually they always match. Any question about this model? Yeah, and if you remove, for example, the assertions that I added, you can see that this way of doing things really simplifies the forward pass. And so you can really see what's going on. And then you can see, oh, what's the conv? Well, it's just a sequential model. So it's a bit better structured than defining everything on the forward pass. Any question? No, okay. Then, as usual, we have the GPU. We designed the GPU. We moved. We define the device if we have a GPU. And Rafael, what's the name of the backend for Mac? MPS. So essentially, if you have a Mac and you want to run the stuff locally, you can do MPS. And this, for the new MacBooks, the one with the Apple Silicon chips, and this will run on the GPU on that chip. So that's something that you might try if you want to run stuff locally. Yeah, then this is the usual training loop, and I don't think there are many things. We just move the model to the device inside the training loop, not to forget, but you can move it outside, but you just have to remember to do it. And if you don't, usually you get an error that if you move the data, but you don't move the, if you don't move the model, you get that the type of the tensors that you're trying to use are not the same, and usually one contains the name CUDA and the other doesn't, and this is usually an indication that you didn't move all the data to the GPU. Yeah. Do you have any question about the training loop? I think we've seen it many times, so it should be. Yeah.
About the dropout stuff.
Yeah.
Training loop.
Yeah.
So on the slides you explained how to enable the dropout still when you're in evaluation.
Mm-hmm. Yeah.
So are we supposed to do that here?
No, that's only if you want to essentially get multiple predictions from your model. but not during training, only during inference, and is a decision that you have to do, that you want to do that methodology to estimate, to get an average of prediction on slightly different models, and then you can get also like a standard deviation of the prediction. But it's not something that you need to do in the loop. In the loop, you just put the model in train mode, the whole model, and here the dropout layers are active, and then when you do the validation, you put it in evaluation mode, so you turn off the dropouts. Yeah, this is okay. And then I think the only different thing is here, where you save the best model. So essentially, you store the best validation loss, and you compare it to the current validation loss, which is in a list. So you take just the last element because you added it here to this list. You appended a new element. So the last one is the current validation loss. And if it's smaller than the best you have seen so far, you store the model state dict in a variable. And then at the end of the training loop, when you finish the number of epochs, you can actually return, well, you can actually reload the best state dictionary into the model. So this is essentially the model at the epoch that had the lowest validation loss. Yeah, and then everything else here, I choose the negative log likelihood loss, because we have the log softmax layer in our neural network for classification. If we didn't use that, then here as a loss function, I would have to use the cross entropy loss. And then, and then we train essentially, well, we instantiate a model with a dropout probability of 0, so it doesn't have any dropout. And we use the train loader without data augmentation. So this is essentially equivalent to what we had in the previous notebook yesterday. And then the other one is training with dropouts, but still on the data set without augmentation. And the last one is actually not using dropouts, but using the data augmentation for your training set. One thing to mention is that the GPUs on Daint is quite an old system, don't have tensor cores. There are specific parts of the GPU that are very good for matrix-matrix multiplication, which are used a lot in convolutional neural network and also the linear layers. And so, yeah, I expected the training to be a bit faster, but it was a bit slow. The next supercomputer that we will have here will have the last generation of GPUs that are really good for deep learning. So if you rerun this notebook on the new supercomputer, when it comes online, it should be lightning fast. So yeah, good progress there. And then if we look at the loss function, you can see that for the standard model, we have the same situation as yesterday, where the validation loss starts decreasing, and then it starts increasing again. So we start overfitting because we keep adjusting the weights of our model to fit the training set, but then it's not able to generalize. While with the dropout layers, which force the model to use different paths in the neural network, essentially acts as a regularizer, and so you don't have this effect of overfitting anymore, and you can see that the validation loss decreases hand-to-hand with the training loss. So this is very good. Because you can continue training. At some point, probably we start increasing again, but here we are at 14 epochs, and here we're already at 13, and you can see that the validation is smaller and not increasing, and probably by training for more epochs, you can still getting it down a bit. And the same thing happens with data augmentation. So they're really good techniques to use when you're training deep learning models. Yeah, and then if you look at the actual metric accuracy of your prediction for the classifier, you can see that without data augmentation, you have, or without dropouts, 70%, and then just by adding 2 dropout layers to your network or doing data augmentation, you can get already like 60 or 6 or 8% better. Do you have any question? No? Yeah.
With the dropout layer, there was a probability of 0.5.
Mm-hmm.
I continue to train at the. I skip more and more of the connections during the it becomes smaller and smaller and smaller.
No, so every time it chooses half of the input to be 0, essentially, and it's always different. So, for example, here, if you have this dropout here, well, this one, for example, you have 512 outputs, and it means that with probability, well, if you use 0.5, 50%, you remove some of this output. And essentially, on average, it means that you will have half less inputs. But every time, you will have half less input. So you apply a new dropout every time, and it's not always the same nodes. And this is what helps, because the model cannot rely on the data going always through the same path into the model. Sometimes, essentially, like some neurons are removed, but they're randomly removed. Is it clear? Okay.